Okay, in this video we're going to go over Chapter 8, Sections 4 to 6, and we start out with prime numbers. Now, prime numbers are very, very important. So you can see I have part of the page showing here. So by definition, prime numbers are the counting numbers greater than 1. Okay, so the text says other than 1, but I'm going to say greater than 1, and that are divisible only by 1 and itself. So the way to remember prime numbers is look at the word prime, and you see how you can see let me just get this color here, I and me. So they only have two factors, 1, that's the I, and me, and the me is itself. So for example, 2, 3, 5, and 7 each have two factors, 1 and 2, 1 and 3, 1 and 5, and 1 and 7 respectively. Okay, by definition, the opposite of prime numbers are composite numbers, and they are counting numbers greater than 1 that are not prime. So think about composite rocks. So if you remember your earth science classes way back in the day, composite rocks are made up of many types of minerals. So for example, the number 4 can be broken down into the factors of 2 times 2 and 4 times 1. And since you have 2 times 2 also, it is not prime. Okay, 6 is 1 times 6. Okay, that would make it prime. But then you also have 2 times 3, so not prime. 8 is 1 times 8. Okay, that's a candidate for prime. But now you have 2 times 4 as well. And 10, 1 times 10, but then you also have 5 times 2. Okay, so composite numbers have factors other than just 1 and itself. Okay, so then we go on to the next paragraph. The prime numbers are considered to be the building blocks of the counting numbers because every single counting number greater than 1 is either prime or can be factored as a product of prime numbers. So for example, 100 is 10 by 10, but that can be factored or represented as the product of 5 times 2 times 5 times 2. Okay, 2009, huge number, can be represented as 41 times 7 times 7. Now 41 is prime, so it only has two factors, 1 in itself, but you also have the 7 times 7. So when you think of prime, you only have two factors, 1 and the number itself. When you think of composite, you have multiple factors. Now, taking things down to their prime factors is one way that we can simplify radicals. For example, so on this page, I'm going to say, let's look at the 100. If I say radical 100, and I want to simplify that, or take it down to its prime factors, I will say 5 times 2 times 5 times 2. And in terms of simplifying a radical, you would identify pairs. The pairs come out as single digits. So 5 and 5 come out of the radical as 5, and 2 times 2 comes out of the radical as 2. Nothing is left in the radical, and therefore the square root may be simplified to 10. So clearly 100 is a perfect square. But in terms of other numbers that are not perfect squares, we can use this prime factorization technique to figure out how to simplify the numbers. Okay, so then we're going to go on to the fundamental theorem of algebra. I'm going to do this on the next slide. So the fundamental theorem of algebra is that every single counting number greater than 1 can be factored as a product of primes in only one unique way. Okay, so that's important to understand. How do we know which numbers are prime? and we can use this sieve treatment. Now this is the sieve of, let's see if we can pronounce this together, Eratosthenes. Okay, so by that sieve, we can determine which numbers are prime, and we'll do that on the next page. So here I have listed the numbers. Let me just make this a little bit bigger. Okay, the numbers are listed that are between 1 and 100. So we know already that by definition, a prime number has to be greater than 1. So I have the 1 there, and that is not being considered as a prime number. So 1 is out. Okay, so 2. 2 is a prime number. In fact, that's the first prime number, and it's the only prime number that is indeed even. So you can see I have some information down here that's color-coded. So I say in my directions, ignore the number 1. It is not a candidate for either being prime or being a composite number. Put a white box around the number 2, and then put a green box about all multiples of 2. So I have my 2, and my green boxes that are multiples of 2, I'm also going to kind of cross out. So out, 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 and I could go all the way down the list. But knowing that all the green boxes are multiples of 2 lets me know that they are not prime. So I don't really need to cancel them out by crossing them out because I already know they're not prime. Okay, then it says put a white box around 3 and then put a blue box around all remaining multiples that are multiples of 3. Okay, so we are going to do that now. Now notice 6 is a multiple of 3, but because it was a multiple of 2, it's already taken care of. So all the blue boxes that you see are only multiples of 3. And because they're multiples of 3, they are not prime. They are not prime. Next, put a white box around 5, and then put an orange box around all remaining numbers that are multiples of 5. Okay, so the orange boxes are the numbers that are only multiples of 5. They're not multiples of 3 or of 2, and they are also not prime. Then we move on. I say put a white box around 7, and then put a purple box around all remaining numbers that are multiples of 7. So the first one we come to looks like 49. Then we have 77. Then we have 91. So all the green, all the blue, all the orange, and all the purple are not prime. All the white are prime. And by definition, prime has only 2 multiples, 1 and itself. So class activity CA 155 also lets you do that. So note that this is an important activity. It helps your students have a sense of what are prime numbers. And in this particular activity, all the prime numbers are white. All the non-primes are colors other than white. Okay, on this page we talk about the trial division method for determining whether a number is prime. So trial division means that you try a division, and if you have no remainder, then the number in question is divisible by the number you tried. So it says instead of using the sieve above, you can divide your number by 2. Then if that doesn't work, try 3. If that doesn't work, try 5, going through all the prime numbers. If you do not find a prime number that divides your number, then and only then is your number prime. So as I said earlier, this method is called the trial division. Class activity CA-156 gives you a way to practice trial division. Trial division often requires patience. For example, a number like 899 may appear prime until you check 29. And then you discover that 899 is not prime because it is a multiple of 29. 29 times 31 is 899, and therefore it has multiples that are not just 1 and itself. It is not prime. Okay, in terms of a graphing calculator application, this is kind of important, so I'm going to start right here. In the equation editor of your graphing calculator, and that's where the y1 appears, if you type in 899 divided by x, and you look at your table, you will see that all the multiples of 899, and look for the whole number multiples, these are your factors. So that's an important technique, because sometimes you have to be very, very patient, and using your calculator helps you to be patient in a very, I guess, instructive way, that you have a tool to work with. Okay, we're going to talk about factoring into products of prime numbers using factor tree on the next slide. Okay, on this slide, you are seeing factoring into products of prime numbers, and this is a convenient way to factor and create a factor tree. So all of the green numbers, they are prime factors. So I say that, note, all the green circles are prime, and therefore prime factorization of 270 is 2, so here's your 2 times 5 times 3 times 3 times 3. If you check this in your calculator and you multiply those 5 terms together, you will indeed get 270 back. Okay, there's a class activity, and it's class activity AC-157 that will reinforce that. So how many prime numbers are there? Okay, the list goes on forever, just like the list of numbers that never end. So let's go on to the next page. Okay, on this page, we are talking about 8.5. And 8.5's title is Greatest Common Factor and Least Common Multiple. Okay, two very important items. So under Greatest Common Factor, which can be abbreviated as GCF, you talk about two or more numbers. So is the greatest counting number that is a factor of all the given counting numbers? So is that determinable? Yes, it is. So, for example, if I ask you to find the greatest common factor of both 12 and 18, so first do 12. The factors of 12 in order from least to greatest are 1, 2, 3, 4, 6, and 12. The factors of 18 from least to greatest is 1, 2, 3, 6, 9, and 18. So the greatest common factor is 6. So 6 I wrote in bold, and it is the largest number that can be evenly divided into both 12 and 18. So 6 goes into 12 2 times, 6 goes into 18 3 times, and 6 is indeed the greatest common factor. Okay, so change your thought process for just a second, and let's think about least common multiple, which is abbreviated as LCM, and it usually pertains to two or more numbers that you are comparing. Okay, is the least common multiple, okay, so the LCM is the least common multiple that is a multiple of all of the given numbers. So let's start with 6 and 8. So 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, 6 times 4 is 24, 6 times 5 is 30, which looks like I skipped, 6 times 6 is 36, 6 times 7 is 42, 6 times 8 is 48, 6 times 9 is 54. Those are the multiples. Look at the multiples of 8. Do you see how I've bolded 24? So 24 is the lowest number. That's a multiple that's common to both 6 and 8. So therefore it is the least common multiple. Okay? We're going to go on the next slide and talk about the slide method for finding GCFs and LCMs. So we have one activity that can be practiced in activity CA-158. And in this one activity, we'll discuss GCFs and LCMs using one technique. Okay, here is the slide method for finding GCF and LCMs of two numbers. So list your two numbers, and our two numbers are 48 and 80. So because they end in 0 and 8, they're divisible by 2. So put a 2 in the outside, right here, and then divide 2 into 48 and 2 into 80, you get 24 and 40. Okay, continue this process, 2 into 24 and 40, go 12 and 20, 2 into 12 and 20, go 6 and 10, and 2 into 6 and 10, go 3 and 5. Okay, on the vertical section right here, all the 2's. 2 times 2 times 2 times 2, what is that? That looks like 16. So the numbers on the outside multiply to 16, and 16 is your greatest common factor. So that is the largest number that goes into both 24. Let me think about this. Goes into both 48 and 60 evenly. So 16 is your greatest common factor. Then look at the horizontal side. We are left with 3 and 5. So what is 3 and 5? How is that helping us? If you want to figure out the least common multiple, what you're going to do is you're going to multiply your GCF, which was 16, that we got by saying 2 times 2 times 2 times 2, and then if you also multiply by 3 and by 5, you will find the least common multiple of 48 and 80. So this is the biggest number that they can both go into evenly, is 240. Then, a neat thing about this is you can take a fraction and reduce it to lowest terms. So if your fraction was 48 over 80, the two numbers are the horizontal, the 3 and the 5. 3 over 5 is that fraction, 48 over 80, represented in simplest terms. So all of this work is important. So look at that and make sure you understand how you get GCF. GCF is the vertical numbers. How you get LCM, vertical times horizontal, and how you get a fraction expressed in lowest terms if your fraction is 48 over 80. So think about that. It's a very, very helpful method, the slide method. Okay, so just to recap, the slide method we just demonstrated can be very helpful in doing certain operations with numbers. So for example, the GCF is used to put the fraction in simplest terms. So the fraction 24 over 36 can be put into simplest terms by dividing the numerator and the denominator by the greatest common factor. And that greatest common factor is 12. So dividing by the greatest common factor gives you a numerator of 2 and a denominator of 3, and this represents the fraction 24 over 36 in simplest form. Okay, LCM, on the other hand, is used to add fractions with different denominators. So let's say, for example, you had 1/6 plus 3/8. The LCM of 6 and 8 is 24. So if you convert 1/6 into 24ths by multiplying by the number 4 over 4, which is equivalent to 1, and then you convert 3/8 into 24ths by multiplying by the number 3 over 3, which is equivalent to 1, you will end up with a sum of 13 over 24. So that is your fraction that you get by adding the two fractions of 1/6 plus 3/8 after having used the LCM to get a common denominator. Okay, so 8.6 is the next section. 8.6 talks about rational and irrational numbers. So rational numbers are numbers that can be expressed as a ratio. So look at the first 5 letters of rational and you see the word ratio. Remember that ratio is equivalent to a fraction. So you can express rational numbers as ratios. They can be positive or they can be negative. Okay, real numbers are those numbers that can be expressed in a decimal representation or the negative of such a number. Okay, irrational now are those numbers that cannot be expressed as a ratio. Examples of irrational numbers are numbers such as pi and e. Both of these numbers are real, but they just cannot be written as a fraction. So you want to understand those vocab words. Okay, when you try to represent a fraction as a decimal, there are 2 types of numbers that you can get. You can get terminating numbers or repeating numbers. So when we use division to write a fraction as a decimal, the decimal representation is of one of those 2 types, either repeating or terminating. So I have this little black box, and the little black box says that a terminating decimal is a decimal that stops or ends or terminates. Okay, an example is 1.25. There are no more digits available, or 0.892. Done. Okay, repeating decimal is a decimal that has a repeating digit or a repeating group of digits. So for example, 1.3333 can be represented as 1.3 with a bar on top. That's called bar notation. So only the 3 in the decimal spot repeats. Versus 1.21212121, etc. So in this situation, it's also a repeating decimal, but now the 10th place and the 100th place repeat. So 0.12 would have the bar notation above. Repeating decimals usually have a bar notation, so you see it that way, or you can see it as the same number repeated over and over again, like we have here, right here, with a dot, dot, dot. Okay, so that's important to note. Okay, using subdivided squares to see decimal representation of fractions. So if you look at figure 8.11 in the text on page 345, you will get a sense of how to graphically represent a repeating number of 1/3. Okay, writing repeating and terminating decimals as fractions. Another method for writing a repeating decimal as a fraction involves shifting the decimal point by multiplying by a single power of 10 and then subtracting so that the resulting quantity is no longer has a repeating component. So we'll do that on the next page. Okay, this page is a rather important page because it demonstrates how to write a repeating fraction, a repeating decimal as a fraction. So we're using n equals 0.123 bar notation as our example. So we can see that if we set up our problem here, we can subtract n from 1000n in this method. So if you say 1000n, that's what you get. If you subtract n from it, look what drops out. The repeating decimal section drops out. So if we do this subtraction over here, we are getting 1000 minus n, so that's going to equal 999n, and that's equivalent to 123, so therefore n, the number that we want to express as a fraction, is equal to 123 over 999. So that means that our bar notation, 0.123, 123 bar is fractionally equivalent to 123 over 999. Okay, here is another example on how you can convert a repeating decimal into a fraction. And this is mimicked in class activity 166. So, if x equals 0.999, so this is an interesting page because it aligns with class activity CA 166. So if you have x, which is equal to 0.99 ... so that means 0.99 goes on forever and ever. So if you take 10 times it, you will get 9.999, okay, because I've added 9 plus 0.999. And then if you subtract away the x, you will end up realizing that 0.999 actually equals 1. So that's kind of a neat little fact. Okay, there's a section on irrationality of the square root of 2 and other square roots. So I've given you this YouTube video, which is very interesting, but know that we are not going to go into a lot of this. This is going to be a little part of discrete math that I'm giving you a glimpse of. We will not, however, do anything with this, but it is rather interesting. So if you have time, please watch this YouTube video. So that ends 8.4 to 8.6, and I'll see you in class, and we'll start Chapter 9.